We've got Dr. Bruce Dale coming up next to grapple with the question of energy security. He's professor of chemical engineering, former chair of that Department of Chemical and Engineering Material Science at Michigan State, principal investigator and faculty advisor for Biomass Conversion Research Laboratory, and he's a fellow of the American Institute of Chemical Engineers and currently the editor-chief of Biofuels, Bioproducts, and Biorefining. I almost said byproducts, and they're not byproducts, they're co-products.
Thank you, sir. So this is a shortened version of a talk that I give that's usually about 45 minutes long. I'm going to hold it strictly to 15 minutes and be off the stage at quarter till so we can have a chance for a good roundtable. If you're not somewhat depressed when I'm done with my talk, then I haven't done my job, because I have to be honest with you and be quite a bit more sober about the ability of our society to provide the energy on which most of our technology has developed. We've heard about wonderful technologies. One of the things that almost all of them have in common is that they require energy to make them work. And the question is, where is that energy going to come from? I've devoted my own attention to how we have food and sustainable biofuels, but I'm probably not going to get to that during this talk. I'll probably just talk about the big picture energy issues. So the thesis I want to propose to you is that renewable energy is critical for human well-being, energy generally, but renewable energy specifically. Let me tell you why. The rate of energy use, which is equivalent, again, I'm happy to have a group of engineers. We know that energy is defined as the ability to do work. So the rate at which we use energy is the rate at which we do work, right? That determines, I think it's the biggest single or best single predictor of how wealthy a society is how much energy it uses, how quickly it uses energy. Every single rich society on the planet uses a lot of energy. About 1/3 of that is oil. Energy efficiency is really important. I don't want to run that down, but it's insufficient as itself. Being energy efficient with a non-renewable resource just means you run out slower. It doesn't mean you don't run out. Okay. Fossil energy use, since about 85% of total world energy use is based on non-renewable fossil energy sources, then about 85% of our current wealth is dependent on a non-renewable resource, and it will end when that fossil resource ends. Okay, again, we can slow it down by being more efficient. We can use other energy sources. We can scrape the bottom of the barrel on the fossil resources, which is what we're doing. But ultimately, we have to face the idea if we want to continue to be prosperous, we have to have very large-scale, sustainable, renewable energy systems. Billions of poor people in the world will never be able to access enough fossil energy to develop their potential because it will be gone in the next few decades. So we need to have renewable energy. We need to have a lot of it, and it needs to happen relatively quickly. It takes decades to roll out energy systems. We should have started in earnest decades ago. We didn't, so we're going to pay a price for that. The sooner we embrace this as something we have to have and have to have quickly, the more quickly we'll make the progress we need. I'm going to specifically talk about liquid fuels and their relationship to petroleum, but all forms of energy are important to us. But again, liquid fuels right now, my emphasis. And people can argue about this. In fact, the economists love to argue about it. If there's an economist here, I'll be glad to insult you later on, but in private. But I've had a very difficult time communicating this with traditional economists who seem to think that resources appear magically out of air when there's a demand for them. Well, we've had a demand for cheap oil for a long time. But $20 a barrel oil is a thing of the past. There's no sign that's coming back. We can want a lot of things, but the biosphere is not obligated to provide those to us. So only large-scale, low-cost, low-carbon energy sources can be simultaneous, and we need to do all these things. We do need to reduce greenhouse gases. We do need to have energy security, and we do need to have long-term sustainable wealth. So biofuels in particular, and these are liquid fuels from plant material, are not optional. We must have them, but they must also become much more sustainable. As I said, I'm only going to be able to focus on the first part of a talk that's actually quite a bit longer. Here are some of the basic data that underlies my thesis. This is a straight line relationship between the per capita primary power consumption, okay, kilowatts per person, rate of energy use, and the GDP per capita. If you break down the units of GDP, it's dollars per year per person, GDP per capita. So directly, the most common measure that we have of wealth is GDP. It's not the greatest perfect measure. It has drawbacks, but it's the one that we use most widely. The correlation coefficient here is about 93%. In other words, 93% of the observed variation between a society's energy use and its wealth production or of variation between different societies is how much energy they get to use. If you use less energy, you're less wealthy. This should not be hard for a group of engineers to understand, but it seems almost impossible for some people to understand who magically imagine, I guess, that the energy that we have or that our wealth just appears from nothing. The wealth appears when work is done on raw materials, bringing them out of the natural world and creating wealth for human beings. Food, fuel, building materials, clothing, whatever else you want to say it. Okay? Consider the implications of this graph. Consider for a moment with me that this actually might be telling us something real about the real world. It's current energy consumption that defines current wealth. If you get more energy, you get to be wealthier. If you get less energy, you get to be poorer. And if this is based on non-renewable resources, then what's the inevitable conclusion? As those non-renewable energy resources become less available, we're going to get poorer. I think you have to accept that data. Again, it's depressing. It's somewhat depressing or sobering. It ought to be sobering. Another important implication that I'm not going to go into is almost all of the societal and economic and political structures of the developed world require and assume that you're going to be richer tomorrow, your GDP tomorrow is going to be greater than the GDP yesterday, so that you can continue to pay for the expensive social programs you promised yesterday, Medicare and Social Security, and go on and on and on. What if that's no longer possible? What if the ability to increase energy consumption, increase wealth consumption, to meet those promises, to pay your bills, to pay the interest on the debt that you already accumulated, what if that's no longer there? I think it will no longer be there, at least not in the quantities we've become accustomed to. And yet we're hardly talking about this, and political people run away from it very quickly, run away from the idea very quickly. So are we just better off when we consume more energy? Well, no. I mean, our abundance of our lives as human beings is determined by a lot of different things, not just energy consumption. So this graph actually provides some hope. Okay? I have to caution you there. Once again, we plot per capita primary power consumption on the x-axis. On the y-axis, we put what's called the Human Development Index, or HDI. This is a composite measure developed by the United Nations that is a composite metric of life expectancy at birth. Life expectancy is important, right? How many years you expect to live. The years of schooling and expected years of schooling that people get, as also the wealth, the GDP. It's a composite measure there. And we see some encouragement here, and that is that people don't continually get better off by consuming more energy, a higher rate of power consumption. In fact, it levels off. And the question is, where does it level off? The answer is at about 2 to 4 kilowatts per capita. Okay? You can get a high Human Development Index by consuming roughly 4 kilowatts per person all the time, every day, right? This is a rate of energy consumption. Germany is at that rate. The United States Germany is roughly 6 kilowatts per person. U.S. is about 12, and Iceland's out there at about 30, okay? So let's do some numbers here. We've heard numbers of 7 to 9 billion people on the planet. If take the lower bound of what seems to be required at about 2 kilowatts per person to get a reasonable level of energy consumption or a reasonable level of human development. 2 kilowatts per person times 7 billion people on the planet equals how much? The answer is 14 terawatt. And the question is, how much energy in all forms did human beings use in recent years? The answer is about 15 terawatt, 85% of it from non-renewable resources. If we're going to provide enough energy for more of the people and most of the people on the planet to lead decent lives, we have to greatly expand energy opportunities. But I think it's totally irresponsible to think that that can or should happen from fossil sources, which are going to run out anyway. We need to be laying the foundations right now, today. We should have done it decades ago. But right now, today, for large-scale renewable energy systems. Otherwise, we can count on becoming poorer, less healthy, and less educated. Okay, I don't think there's any escaping that data. Okay, 7 minutes left. Okay, I've often asked about energy efficiency. Again, energy efficiency is really important, but it's not enough. And why is it not enough? Well, look at this graph again. This time on the y-axis, or the x-axis, I plotted its logarithmic plot of the per capita primary energy consumption. Again, thanks. Really glad to talk to engineers who know about logarithms, right? I don't have to explain that every unit down there is a 10-fold increase. But the point I want to draw to you is that there's this is something like 156 countries in this database, and it once again shows the Human Development Index as a function of their rate of energy consumption. And the point I want to make is that no society on this planet has figured out how to have a high Human Development Index, high levels of human development, and simultaneously use just a little bit of energy. I'm talking about a tenth or 100th of a kilowatt per person. Apparently we need a couple of kilowatts per person, and those are not going to come long term. They're not even going to come from oil in the shorter term, from fossil resources. We have to figure out renewable sources. I'm going to go through this rather quickly. It's actually not energy that we're after, it's the services that energy provides. Those are heat to keep us warm, light or electricity, and mobility services. Where do they come from? Well, they come from coal, natural gas, and for mobility, almost exclusively, it's oil. All energy services aren't created equal. We actually value mobility more than any other energy service. Electricity and batteries are important, but they can't meet more than about half of our total mobility needs, and they can't support commerce at all. Commerce moves by trucks, ocean shipping, rail, and jet aircraft, all of which physically require high energy density liquid fuels. Okay, so where are those high energy density liquid fuels going to come from on a renewable basis? The only sustainable way I know to produce high energy density liquid fuels is from plant material or biofuels. So I'm saying this as the proud owner of a Chevy Volt. I love my car. And I'm getting, after 2.5 years of driving it as a regular vehicle, 93 miles per gallon. Okay, that's great, but it's not 900 miles per gallon. I've stretched the oil supply, I've made it more useful, but I haven't eliminated. In 2.5 years, I used about 250 gallons of gasoline. Okay. The United States peaked in our oil consumption in 2007 at about 21 million barrels a day. By 2011, that was down to 19 million barrels a day, a decline of about 9%. Our per capita median U.S. household income also declined about 8% between those 2 years. Some people think that's just a coincidence. I don't. I think they're a very strong relationship, that people are less wealthy because they have less access to energy. And so here is perhaps the grim news, and I'll just go to the bottom line here. This is a stacked graph showing oil production, world oil production from different parts of the world. The data go back to actually 1900. In 1900, the world consumed about 20 million metric tons of oil. In 2005, the world consumed approximately 4,000 million metric tons of oil, 4 billion metric tons of oil. In other words, world oil consumption has grown by a factor of 200 over the past century. Since 2005, it has not grown at all. Okay? And in fact, if you look at conventional oil production, it's actually decreased slightly. That slight rise, the bump that you see there, is as a result of redefining what's oil. And that includes things like the tar sands, oil from tight shales. And by the way, I'll just say it here without just, we can talk about it at the panel discussion time. The tight shale, if you actually look at the details, not just believe the hype that the people who are selling you the stock want to publish, the oil from tight shales is a blip on a downward decline because those wells decline in their initial rate of production by 80 or 90% over the first few years. They frack them, they break it open, and the oil comes out very fast for just a couple of years, and then it's essentially gone. Okay, that's the real story of oil. And I can talk to you about the Monterey Shale, on which the Energy Information Agency was counting for about half of our tight shale production. They've reduced the potential production from the Monterey Shale by 94% because of technical reasons. Okay, so I'm glad we have it. I hope we'll use it wisely to help establish a renewable energy industry. But we are at peak oil, folks. Okay, we have already passed it. It happened several years ago. It shouldn't be surprising to anybody who understands a little bit about the physics of oil production. This is the iconic oil state. This is the annual oil production in Texas in thousands of barrels. Peaked in 1970, has been declining ever since. It's about at 1/3 of what its peak production was. Alaska crude oil production, okay, same sort of thing, rapid rise followed by a decline, also about 1/3 of what it was. This is the same for every oil field in the world. In the world, oil production is the sum of all the oil fields in the world. Okay, we're consuming roughly 3 barrels of oil for every new barrel of oil we discover, and that's reality. As you might expect from that, the comparative value of different energy sources has diverged. On a dollar per gigajoule basis, oil is worth now about 5 times as much as a gigajoule of natural gas. 3 times as much as a gigajoule of natural gas, and about 5 times as much as a gigajoule of coal. So the question is, where's our fuel future going to come from? Is it going to come increasingly? No insult to our Canadian hosts here, but this is ugly. I grew up in a mining town, a copper mining town in Nevada. This is what a mining industry looks like. Do we want to mine, continue to mine, or we want to continue to try to go for something that's more renewable and sustainable? I like the idea of developing sustainable sources of fuels and feeds and foods based on plant material. And hopefully we can talk about that a little bit. This talk was going to get more hopeful at about this point, but unfortunately I have to leave you depressed, and we'll look forward to the conversation later on. So 15 minutes and I'm out of here. Thanks.
Quick question, one question. Right up front.
Is there anything you have to follow when looking at that data? Iceland, Norway, did those countries consciously do anything to be carbon investors, or just energy and
Iceland sits on the large geothermal reserve, back volcanoes, and they are able to use a lot of energy because it's geothermal. Norway has its declining North Sea oil reserves as their source. So Iceland's got renewable, but dangerous or potentially disruptive, and Norway has a non-renewable.
Great, thanks.